Look up at the night sky, and what do you see? A scattering of stars, maybe a planet or two, but hidden in that vast darkness are some of the universe's most tightly kept secrets. Among them, star clusters, those glittering knots of stars bound together by gravity, hold stories so strange they defy everything we think we know about space. Some of these clusters shouldn't exist. Others behave in ways that leave scientists utterly baffled. And today, we're diving deep into 30 of the most jaw-dropping discoveries about these cosmic enigmas, revelations that will make you question what's really out there. Imagine a place where stars are packed so densely they're practically shoulder to shoulder, where newborn stars blaze alongside ancient ones, and where the laws of physics seem to twist into something unrecognizable. These aren't just hypotheticals, they're real phenomena happening right now in star clusters across the galaxy. Some of them contain stars older than the universe itself, at least according to our current calculations. Others have missing black holes, rogue planets drifting between stars, or mysterious forces pushing them apart in ways we can't explain. It's like the universe decided to throw the rulebook out the window and leave us scrambling to make sense of it all. This isn't just science, it's a detective story written in starlight. Every discovery we'll explore today unravels another thread of the cosmic tapestry, revealing just how much we still don't understand. From ghostly clusters that vanish without a trace to stars moving in perfect, impossible synchronization, these mysteries challenge our very understanding of space and time. So if you're ready to have your mind stretched by the universe's strangest quirks, buckle up, because what we're about to uncover isn't just fascinating, it might just change how you see the night sky forever. Deep within a star cluster called Messier 5, lurking about 7,500 light-years from Earth, there's an object so violent it could belong in a cosmic horror story. Astronomers call it the Black Widow Pulsar, a name that perfectly captures its deadly nature. This incredibly dense, rapidly spinning neutron star is methodically tearing apart its companion star, blasting it with radiation so intense it's evaporating the star's outer layers into space. And just like its namesake spider, once it's done, there'll be nothing left. What makes this object truly bizarre isn't just its destructive behavior, it's the staggering energy involved. The pulsar emits beams of gamma rays so powerful they're detectable across interstellar distances, flickering like a sinister cosmic lighthouse. Scientists first spotted this phenomenon in the late 1980s, but even now, decades later, its extreme physics defies easy explanation. Normally, pulsars slow down as they age, but this one seems to defy the rules, spinning hundreds of times per second with eerie precision while cannibalizing its neighbor. The companion star isn't going quietly, though. As the pulsar's radiation strips away its atmosphere, the stolen material forms a swirling disk of superheated plasma around the neutron star, occasionally triggering violent outbursts that light up telescopes across multiple wavelengths. Some researchers think the system might even be producing antimatter in these chaotic interactions, something almost unheard of in typical star clusters. But here's the real kicker: the Black Widow pulsar shouldn't exist in a cluster this old. Star clusters like Messier 5 are ancient relics packed with stars that formed over 12 billion years ago. Yet this pulsar behaves like something born from a much more recent supernova. Did it somehow form later, or is there a hidden mechanism keeping it spinning far longer than physics predicts? Either way, it's a reminder that even in the crowded stellar metropolises of the cosmos, there are still monsters lurking, waiting to upend everything we think we know. In the sprawling tapestry of the cosmos, dark matter is supposed to be the invisible glue holding everything together, yet some star clusters are flipping that idea on its head. Take NGC 6101, a globular cluster drifting through the outskirts of the Andromeda Galaxy. Unlike nearly every other structure in the universe, this dense knot of stars shows zero evidence of dark matter's gravitational influence. That's not just unusual, it's like finding a skyscraper with no foundation, defying every expectation of how these cosmic structures form. The mystery only deepens when you consider how globular clusters are thought to work. Most of them orbit galaxies like satellites, held in place by the gravitational pull of dark matter. But NGC 6101 and a handful of others move as if that unseen force simply doesn't exist. Their stars whirl around one another purely through their own gravity, like dancers in a tightly choreographed routine with no external conductor. Some astrophysicists argue these clusters might have been stripped of their dark matter by galactic tides, but simulations show that process should tear the cluster apart entirely, yet here they are, perfectly intact. Then there's the timing problem. These rogue clusters are old, ancient, even with stars dating back to the early universe. If dark matter was never part of their story, it challenges the leading theories of how the first structures in the cosmos emerged. Could they have formed in a rare pocket of space where dark matter was mysteriously absent? Or is there some exotic physics at play that we haven't even considered yet? Every observation raises more questions than answers. Even stranger, a few of these clusters appear to be speeding up as they move, as if propelled by some unseen force, the opposite of what dark matter's drag should cause. It's moments like these that remind us the universe isn't just hiding secrets in the darkness between stars. Sometimes the absence of something we expect to be there is the most baffling clue of all. Omega Centauri isn't your average star cluster, it's a behemoth, a chaotic metropolis of over 10 million stars crammed into a relatively small pocket of space. But amid that stellar chaos, something extraordinary is happening. Stars are flinging themselves outward at speeds that defy logic. These aren't just fast-moving stars, they're runaways streaking through space like cosmic fugitives, some clocking in at over 150,000 miles per hour. That's fast enough to cross the entire United States in under 10 seconds, and the reason behind their escape, it's either a gravitational slingshot from a hidden black hole or something even stranger. Picture this: deep within Omega Centauri, stars are constantly jostling for position, pulled by the collective gravity of millions of neighbors. In this stellar mosh pit, close encounters are inevitable. When two stars swing too close, the gravitational dance can fling one outward like a stone from a sling. But some of these runaway stars are moving too fast for that explanation alone. That's where the black hole theory comes in specifically, a potential intermediate mass black hole lurking at the cluster's core. Unlike the supermassive black holes found in galactic centers, these mid-sized monsters would pack just enough punch to accelerate stars to extreme velocities without completely shredding them. Yet here's the twist: despite decades of searching, astronomers haven't found definitive proof of such a black hole in Omega Centauri. The gravitational fingerprint is there, but the culprit remains invisible. Some researchers argue the cluster might instead harbor multiple smaller black holes, their combined chaos launching stars like a cosmic pinball machine. Others suggest these speed demons could be relics of a dwarf galaxy, Omega Centauri, swallowed long ago, their trajectories scrambled by the violent merger. But the most mind-bending possibility, these stars might not be runaways at all. Instead, they could be intruder stars born outside the cluster, captured during a close encounter, and now hurtling through on unstable orbits. If true, it would mean Omega Centauri isn't just ejecting stars, it's stealing them too. Whatever the explanation, one thing's clear. In a universe where gravity usually keeps things orderly, Omega Centauri's runaway stars are a thrilling exception, a reminder that even the oldest, most crowded places in space still have the power to surprise us. Hidden among the ancient stars of old globular clusters, astronomers keep finding cosmic imposter stars that glow with the vibrant blue hue of youth, surrounded by neighbors billions of years older. These are blue stragglers, stellar anomalies that burn hotter, brighter, and bluer than they have any right to be. And their existence isn't just a curiosity, it's a direct challenge to our understanding of how stars evolve. Picture a retirement home where every resident is over 100 years old, except for one person who looks and moves like they're in their 20s. That's essentially what blue stragglers are doing in clusters like Messier 30 or NGC 362 stellar environments where every other star should have aged into red giants or cooling dwarfs billions of years ago. So how are these youthful-looking rebels defying the cosmic clock? The leading theory involves stellar theft. In the crowded core of a globular cluster, stars brush past each other constantly, and sometimes they don't just pass by. Two aging stars might collide, merging their hydrogen fuel into a single, hotter, more massive star that reignites nuclear fusion with renewed intensity. It's like tossing two half-burned logs together in a fire. Suddenly, the flames surge higher. Hubble Space Telescope observations have even caught blue stragglers with unusual chemical compositions, their outer layers mixed from the violent merger that created them. But mergers aren't the only explanation. Some blue stragglers might be part of binary systems where one star siphons gas from its companion, effectively rejuvenating itself by stealing fresh fuel. Imagine a vampire star growing younger as it drains its neighbor's lifeblood. In clusters like 47 Tucani, astronomers have spotted blue stragglers with suspiciously close companions, evidence that this cosmic cannibalism is at play. Yet the mystery deepens when we find blue stragglers in places where collisions should be rare, like the sparse outer regions of clusters. If they didn't form through mergers or theft, what's keeping them blazing so brightly? Some researchers suggest these outliers might be immigrants, captured from outside the cluster after forming elsewhere. Others speculate about exotic stellar physics, like suppressed convection or magnetic fields locking in their youthful energy. Regardless of their origin, blue stragglers are more than just stellar oddities. They're living proof that even in the oldest corners of the universe, stars can cheat time. And for astronomers, that makes them invaluable. By studying these cosmic Benjamin buttons, we're unlocking secrets about stellar evolution, cluster dynamics, and the chaotic dances that shape the lives of stars. So the next time you gaze at a globular cluster, remember, not everything there is as old as it seems. Some stars are just very, very good at pretending. Palomar 5 should be teeming with red giants, those bloated, aging stars that glow like embers in the twilight of their lives. Yet when astronomers peer into this ancient globular cluster, they find a puzzling absence. It's as if someone plucked out every red giant and left behind only the faint, cooler stars, turning what should be a vibrant stellar retirement home into a ghost town. This isn't just a minor discrepancy, it's a glaring anomaly that hints at a violent history, one that might rewrite our understanding of how star clusters die. The mystery starts with simple math. In a typical globular cluster like Palomar 5, roughly 1 in every 100 stars should be a red giant, their swollen radii and intense brightness making them easy to spot. But here, the numbers don't add up. Some studies suggest Palomar 5 has as few as half the expected red giants, a deficit so stark it can't be chalked up to observational error. So where did they go? One possibility is downright sinister. The cluster might be unraveling from within, its stars being systematically stripped away by the Milky Way's gravity. Palomar 5 orbits our galaxy on a long, looping path that regularly plunges it through the dense disk of the Milky Way. Each close pass acts like a gravitational sieve, shaking loose the cluster's outermost stars, especially the red giants, whose sheer size makes them vulnerable to tidal forces. Over billions of years, this relentless tug of war could have selectively ejected the very stars we'd expect to see, leaving behind a skeleton crew of smaller, more resilient stars. But there's a twist. Recent simulations show tidal stripping alone can't fully explain the red giant shortage. That's led some scientists to suspect an unseen accomplice, a swarm of stellar mass black holes lurking in the cluster's core. These invisible predators would act like gravitational wrecking balls, flinging stars, particularly the larger, slower-moving red giants, out of the cluster entirely. If true, it would mean Palomar 5 isn't just fading quietly into the night. It's being hunted from within, its missing giants casualties of an invisible war. Yet the most startling clue might lie in what is there. Palomar 5 is unusually rich in something called blue horizontal branch stars, hot, helium-burning objects that are typically rare in globular clusters. These stars are the products of extreme stellar evolution, often forming when a red giant loses its outer layers prematurely. Some researchers think this points to a past where Palomar 5 was far denser, with frequent stellar collisions or close encounters that literally ripped the atmospheres off red giants, leaving behind these bizarre blue remnants. What's clear is that Palomar 5 isn't just an oddball, it's a cosmic crime scene, and every missing red giant is a clue. Whether it's being torn apart by the galaxy, ravaged by black holes, or reshaped by ancient collisions, this cluster is showing us the violent, chaotic processes that govern the lives and deaths of these stellar families. And as we piece together its story, we might just uncover secrets about how all clusters meet their end. In the constellation Cancer, nestled among the stars of the open cluster Messier 67, there's a cosmic duet playing out, one that pulses with the rhythm of a heartbeat. These aren't ordinary stars, they're heartbeat stars, binary pairs locked in such an intimate gravitational embrace that their mutual pull stretches and squeezes them like cosmic accordions. Every orbit they brighten and dim in perfect sync, a celestial metronome ticking with eerie precision. And what makes them truly remarkable isn't just their rhythmic flickering, it's what they reveal about the hidden forces shaping stars in crowded clusters. Take the system known as M67S1288, a pair of stars separated by just a few million miles, close enough that their gravitational tides distort each other into egg-shaped ovals. As they whirl around each other every 31 days, their surfaces bulge outward at closest approach, then relax as they pull apart. This relentless flexing heats their outer layers, causing their combined light to surge by nearly 10% at peak brightness. It's as if the stars themselves are breathing, their luminosity rising and falling with each gravitational sigh. But the real magic lies in the details. Unlike typical eclipsing binaries where one star simply passes in front of the other, heartbeat stars flicker because of their shape, not their position. Telescopes like Kepler have captured their light curves in exquisite detail, tracing smooth, sinusoidal waves that look eerily like an electrocardiogram readout. These patterns are so precise, astronomers can use them to map the star's internal structures, almost like stellar ultrasound. The way they vibrate in response to tidal forces reveals hidden properties: density, composition, even the strength of magnetic fields churning beneath their surfaces. Yet here's the puzzle: heartbeat stars are vanishingly rare in most of the galaxy. So why does Messier 67, a cluster over 4 billion years old, host so many of them? The answer might lie in the cluster's unique history. Open clusters like this one are less densely packed than globular clusters, giving stars more room to form wide binary systems. But over millennia, gravitational interactions with neighbors gently nudge these pairs closer together, tightening their orbits until tidal forces take over. It's as if the cluster itself is a matchmaker, orchestrating these cosmic dances through slow, persistent whispers of gravity. Even stranger, some of these systems show signs of misaligned spins, one star rotating horizontally while its partner spins vertically. This odd configuration suggests violent past encounters, perhaps with a third star that knocked the system askew before being ejected entirely. That would make heartbeat stars not just curiosities, but living records of the chaos simmering beneath a cluster's serene appearance. For astronomers, these pulsing binaries are more than just pretty anomalies. They're natural laboratories offering a front row seat to processes that normally play out deep inside stellar cores. By studying how they oscillate, researchers can test theories of tidal heating, angular momentum transfer, and even the eventual fate of binary systems. Will these stars spiral closer until they merge, or will the cluster's gravity someday tear them apart? Every flicker holds a clue. So the next time you look at the night sky, remember, some stars don't just shine. They sing, and in their rhythmic glow, they're whispering secrets about the forces that bind the universe together. Buried in the depths of the globular cluster Messier 4, some 5,600 light-years from Earth, there's a world unlike any other, a planet that might literally be one enormous diamond. This isn't science fiction. It's the bizarre reality of Pulsar Jones 71445459036b, a carbon-rich planet orbiting a pulsar with such extreme conditions. Its very composition defies the limits of our imagination. The story begins with the pulsar itself, a rapidly spinning neutron star that emits beams of radiation like a lighthouse. When astronomers first detected rhythmic pulses from this object in the late 1990s, they noticed tiny, regular inconsistencies in its signal. Something was tugging on the pulsar, subtly warping its rotation. That something turned out to be a planet roughly the size of Jupiter, but with a density so high, it couldn't possibly be made of rock or gas alone. The math pointed to something extraordinary. A world composed primarily of crystalline carbon, in other words, diamond. How does such a planet form? The leading theory is as dramatic as the discovery itself. Billions of years ago, the pulsar was likely part of a binary system with a massive, carbon-rich star. When that star reached the end of its life and exploded in a supernova, the blast stripped away its outer layers, leaving behind a dense core of oxygen and carbon. Under the intense heat and pressure of the explosion, the carbon crystallized, hardening into a diamond-like structure. The pulsar, born from the same cataclysm, now orbits this glittering remnant, locked in a gravitational dance that has lasted millennia. But here's where it gets even stranger. The planet's surface temperature is estimated to hover around 2,700 degrees Fahrenheit, hot enough to melt steel, yet not nearly enough to liquefy diamond, which requires temperatures exceeding 6,500 degrees. That means this world could have vast plains of solid diamond crust, with molten carbon rivers carving valleys into its unthinkably hard landscape. Some models even suggest the interior might harbor exotic forms of carbon, like nanodiamond or lonstellate, materials so tough they make earthly diamonds seem soft. Yet the real mystery isn't just the planet's composition, it's how it survived at all. Globular clusters like Messier 4 are chaotic environments where gravitational interactions between stars should rip planets from their orbits. For this diamond world to persist, it must have formed after the cluster's most violent era, or somehow clung to its pulsar through sheer gravitational tenacity. Either scenario challenges our understanding of planetary formation in such hostile regions. What's more, the pulsar's intense radiation bathes the planet in a relentless stream of high-energy particles, creating an atmosphere, if it has one of ionized carbon vapor. Imagine auroras made not of nitrogen and oxygen, but of glowing, electrified diamond dust. It's a spectacle no human eye will ever witness firsthand, but one that ignites the imagination. This discovery does more than just add a glittering oddity to the cosmic menagerie. It forces us to reconsider the diversity of planets that might exist in the universe, worlds forged not in the gentle nurseries of young stars, but in the ashes of stellar violence. If diamond planets can form in the turbulent hearts of globular clusters, what other unimaginable treasures might be hiding among the stars? NGC 6791 shouldn't exist. At least not the way we see it today. This ancient star cluster tucked away in the constellation Lyra is a cosmic paradox, a gathering of stars twice as old as our solar system, yet brimming with elements that only form in the violent deaths of much younger stars. It's as if these stars discovered the secret to eternal youth, their chemical makeup defying the natural order of the universe, and the closer astronomers look, the stranger the story gets. Most globular clusters are relics of the early universe. They're stars forged from the pristine hydrogen and helium that filled the cosmos after the Big Bang. But NGC 6791 breaks all the rules. Its stars are laced with heavy elements like iron, calcium, and even traces of europium, materials that shouldn't be here in such abundance. These elements are forged in supernova or the collisions of neutron stars, events that take generations of stellar life and death to produce. Yet somehow, this cluster, born when the universe was barely 2 billion years old, has stars enriched with metals at levels rivaling neighborhoods near our modern-day Milky Way. So how did these ancient stars get so polluted? One theory suggests NGC 6791 wasn't always the sparse cluster we see today. It might have once been the heart of a dwarf galaxy, a dense nucleus surrounded by swirling arms of gas and stars. In that environment, multiple generations of stars could have lived and died, seeding the cluster with heavy elements before the galaxy's outer regions were stripped away by tidal forces. It's like finding a medieval castle with electric wiring, evidence of a hidden, more complex history. But the plot thickens. Among these metal-rich stars, astronomers have spotted anomalies that don't just hint at a violent past, they suggest ongoing cosmic alchemy. A significant fraction of the cluster's stars are blue stragglers, those same rejuvenated stars we've seen elsewhere, but here they're mingling with subgiants that burn hotter and brighter than their age should allow. Even more perplexing are the millisecond pulsars, neutron stars spinning hundreds of times per second, their acceleration likely fueled by stolen material from nearby companions. These aren't just relics, they're active participants in a cycle of stellar rebirth. Then there's the lithium problem. Most old stars show little lithium. It's easily destroyed in their fusion furnaces, but NGC 6791 stars have too much of it. Some process perhaps fresh lithium produced by cosmic rays or exotic nuclear reactions in binary systems seems to be replenishing it. It's as if the cluster has its own stellar pharmacy, dispensing the cosmic equivalent of anti-aging serum. What makes this cluster truly extraordinary isn't just its defiance of time, but the questions it forces us to ask. Are we looking at a freak accident of cosmic evolution or evidence of processes we've yet to understand? Could other, immortal clusters be hiding in plain sight, their secrets overlooked because we assumed old stars should act their age? Every observation peels back another layer, revealing a universe far more dynamic and far stranger than we ever imagined. NGC 6791 isn't just a cluster. It's a time capsule, a crime scene, and a laboratory all in one, a place where the universe's oldest stars are still writing their own rules. And for astronomers, that makes it one of the most valuable puzzles in the sky. Globular cluster M15 should be hiding a monster, based on the frenetic dance of its stars swirling faster and faster as you near its core. There's something massive lurking in its heart, something with the gravitational pull to whip those stars into a cosmic frenzy. The math points to an intermediate mass black hole, a celestial predator weighing in at around 4,000 suns. But here's the problem. After decades of searching, astronomers still can't find it. This phantom black hole has become one of the most stubborn mysteries in modern astrophysics, a cosmic hide-and-seek game where the stakes are nothing less than our understanding of how black holes grow. The evidence for this invisible behemoth starts with motion. Stars near M15's core move at blistering speeds, their velocities increasing the closer you get to the center, a classic sign of a concentrated mass warping spacetime. Hubble Space Telescope observations have clocked these stars at over 60,000 miles per hour, trajectories so tight and fast they'd be impossible without an unseen anchor. Yet when scientists train their instruments on the cluster's heart, searching for the telltale X-ray glow of infalling gas or the subtle wobble of a black hole's accretion disk, they find nothing. No light, no radiation, just eerie silence where a black hole's presence should scream. This absence has sparked a firestorm of debate. Some researchers argue the black hole might simply be dormant, having devoured all nearby matter and now lurking in hibernation. Others propose it's not a single black hole at all, but a swarm of smaller ones, stellar mass remnants packed so densely they mimic the gravitational signature of something larger. There's precedent for this. In dense clusters, black holes tend to sink toward the center over time, their collective mass creating a similar gravitational footprint. But simulations show this scenario should also fling stars outward in predictable patterns that don't quite match M15's stellar choreography. Then there's the timing problem. Intermediate mass black holes are thought to be the missing link between stellar mass black holes and the supermassive giants at galaxy centers. If M15's phantom is real, it would be a pristine example of this elusive class, yet its refusal to reveal itself leaves a gaping hole in the theory. Some astronomers have even floated the idea that we're seeing the ghost of a past black hole, one that evaporated or was ejected in a violent interaction, leaving behind only gravitational scars. But perhaps the most tantalizing clue lies in the cluster's pulsars. M15 hosts several rapidly spinning neutron stars, and their precise ticks act as cosmic metronomes, sensitive to even the slightest gravitational tugs. One pulsar, in particular, orbits so close to the cluster's core that its timing should betray the black hole's presence, yet its pulses remain eerily regular, as if nothing massive is there at all. This isn't just a scientific puzzle, it's a cosmic irony. M15 is one of the first places astronomers expected to find an intermediate mass black hole, a textbook candidate based on its density and age. Yet the harder we look, the more it slips away, forcing us to question whether we've misunderstood black holes, star clusters, or both. Until we solve this mystery, M15 remains a cosmic paradox, a place where the rules of gravity insist something must be lurking, and the universe responds with nothing but silence. Deep in the heart of the Milky Way, buried within one of its densest star clusters, lies a cosmic ticking time bomb, or rather, several of them. Terzan 5, a globular cluster packed with stars so tightly they could practically touch, is home to some of the most erratic pulsars ever discovered. These spinning neutron stars should be the universe's most precise clocks, their radio pulses ticking with atomic clock regularity. But here, they're anything but predictable. Without warning, some of these pulsars suddenly speed up or slow down, as if their internal mechanisms have short-circuited. Astronomers call these events glitches, and in Terzan 5, they're not just occasional hiccups, they're full-blown cosmic tantrums. What makes these glitches so baffling isn't just their frequency, it's their sheer intensity. In most of the galaxy, a pulsar might change its spin rate by a fraction of a percent over years. But in Terzan 5, some pulsars have been caught altering their rotation speeds by hundreds of times that amount in mere days. One particularly rebellious pulsar, known as Pulsar Jones 743-2443 AD, once sped up by a staggering 0.0003 seconds, a seemingly tiny shift. But for an object as precise as a pulsar, it's the equivalent of a mechanical watch suddenly gaining an hour overnight. The leading explanation for these disruptions lies in the pulsar's unfathomably dense interiors. Beneath their solid crusts, a lattice of iron nuclei packed so tightly they form a crystalline structure. Neutrons swirl in a bizarre quantum fluid state. When this superfluid's rotation drifts out of sync with the crust, it can abruptly transfer angular momentum, causing the entire star to jerk forward or backward like a spinning top knocked off balance. Think of it as a cosmic version of an earthquake, where the star's rigid surface cracks under internal stress, releasing pent-up energy in a sudden, violent tremor. But Terzan 5's pulsars throw an extra twist into the mix, their environment. This cluster is a gravitational pressure cooker, with stars crammed so close together that close encounters are inevitable. Some researchers speculate these pulsars might be getting kicked by passing neighbors, their delicate spins disrupted by gravitational nudges we can't yet detect. Others wonder if the cluster's intense magnetic field, stronger than average for such regions, could be warping the pulsar's internal dynamics, turning them into cosmic misfits. Then there's the wildcard theory, microscopic mountains on the pulsar's surfaces. Neutron stars are so dense that even a tiny deformation, a bump no taller than a few millimeters, could create asymmetries in their rotation. Under Terzan 5's extreme conditions, these imperfections might grow until the star can no longer spin smoothly, triggering a glitch. The implications stretch far beyond Terzan 5. If we can decode why these pulsars misbehave so dramatically, we might unlock secrets about the very nature of matter under extreme pressures, conditions so harsh they can't be replicated in any lab on Earth. And that's what makes these glitching pulsars more than just celestial oddities. They're laboratories unto themselves, pushing the limits of physics with every erratic pulse. So while they might frustrate astronomers seeking perfect cosmic timekeepers, they're giving us something far more valuable, a window into the universe's most extreme states of matter. Imagine looking at a family photo where half the relatives are mysteriously missing, no explanation, no clues, just empty spaces where people should be. That's exactly what astronomers see when they study the Hertzsprung-Russell diagrams of certain star clusters. These charts, which plot stars' brightness against their color, should show smooth, predictable patterns as stars age. But in clusters like Messier 3 and Messier 13, there are glaring gaps, entire sections of the diagram where stars should be, yet aren't. It's as if the universe hit the delete button on specific stages of stellar evolution, leaving scientists scrambling to figure out why. These gaps aren't random. They appear in the so-called horizontal branch, a phase where stars burn helium in their cores after exhausting their hydrogen fuel. Normally, this region should be densely populated with stars of varying temperatures and luminosities. But in some clusters, there's a stark desert, a stretch where almost no stars exist, followed by a sudden resurgence on the other side. It's like a bridge with a missing section. You can see where it starts and where it picks up again, but the middle has vanished without a trace. One leading theory points to stellar physics gone haywire. As aging stars shed their outer layers, the remaining core's composition can dramatically affect its behavior. If a star loses just a tiny bit more mass than usual during this process, the helium burning phase might become unstable, causing the star to leapfrog over the gap entirely. Picture a pendulum swinging normally, then suddenly, without warning, teleporting from one side to the other, skipping the middle entirely. That's essentially what these stars might be doing, their internal nuclear reactions short-circuiting their expected evolution. But here's where it gets complicated. The gaps only appear in some clusters, suggesting an environmental factor at play. Take NGC 2808, a globular cluster with a textbook-perfect horizontal branch, no gaps whatsoever. Compare it to NGC 6661, where the horizontal branch looks like it's been nibbled on by cosmic termites. The difference, metallicity. Clusters with higher concentrations of heavy elements tend to show these gaps more prominently, as if the extra metals are destabilizing the star's internal engines. Then there's the wildcard stellar collisions. In densely packed clusters, stars frequently bump into each other, merging or stripping material away. These violent encounters could eject stars from their usual evolutionary tracks, creating voids in the diagram where they should be. Some researchers even speculate that hidden black holes or dark matter might be subtly altering stellar lifespans, though that remains firmly in the realm of speculation for now. What makes these gaps so tantalizing is what they reveal about the limits of our knowledge. The Hertzsprung-Russell diagram is supposed to be the Rosetta Stone of stellar astronomy, a universal key to understanding how stars live and die. But these blank spaces are a humbling reminder. The universe doesn't always follow the rules we've written. Every missing star is a question mark, a silent challenge to uncover the hidden physics shaping these cosmic families. And until we do, those gaps will keep staring back at us, empty, enigmatic, and utterly irresistible. NGC 188 might look like just another ancient star cluster at first glance, but lurking among its elderly stellar residents are cosmic vampire stars that refuse to age gracefully. These aren't your typical celestial objects. They're masters of theft, siphoning gas from their companions to reverse the clock on their own evolution. Scientists call them blue stragglers, but in this cluster, they've taken their survival strategy to an extreme, turning binary systems into scenes of celestial vampirism. The process is as dramatic as it sounds. Picture two stars locked in a close orbit, one a bloated, aging giant, the other a smaller but greedier partner. Over time, gravitational pull strips material from the larger star's outer layers, funneling it onto the surface of the smaller one. This stolen hydrogen fuel reignites nuclear fusion with fresh intensity, causing the thief to burn hotter, brighter, and bluer than stars of its age should. It's like watching a senior citizen suddenly start running marathons after stealing their neighbor's youth serum. But NGC 188's vampires are special even among blue stragglers. Most clusters see this behavior in their densest regions, where stars are packed tight enough for frequent theft. Here, though, these rejuvenated rebels are scattered throughout, a puzzle that suggests the cluster's dynamics are far more complex than we thought. Some might be the product of outright stellar mergers, where two stars collided and fused into a single, hotter object. Others could be the survivors of chaotic three-star encounters, where gravitational tugs ejected one star and left the remaining pair locked in a predatory embrace. Hubble Space Telescope observations reveal even stranger details. The vampiric stars in NGC 188 often show abnormal chemical signatures, their surfaces contaminated by the processed helium and carbon dredged up from their victims' cores. It's forensic evidence of cosmic cannibalism written in the star's very atmospheres. And because this cluster is unusually isolated, far from the Milky Way's disruptive tides, these binary systems have had billions of years to perfect their predatory dance without interruption. Yet the biggest mystery isn't how these stars steal, it's why some victims survive at all. In most cases, the donor star should be completely drained, leaving behind a lifeless husk. But NGC 188 hosts several wounded giants still orbiting their vampiric partners, their outer layers partially intact. This suggests the theft happens in slow, controlled bursts, like a vampire carefully sipping rather than gulping. The result, a bizarre cosmic symbiosis where both stars defy expectations, one clinging to life while the other thrives on its stolen vitality. What makes these vampires so valuable to astronomers isn't just their eerie behavior, it's the window they offer into stellar evolution's dark corners. By studying how they manipulate their lifespans, we're glimpsing processes that could explain anomalies in other clusters, or even illuminate how stars might behave in the universe's most extreme environments. After all, if stars can cheat death by stealing, what other cosmic rulebooks might be waiting to be rewritten? NGC 188's vampires are more than celestial oddities. They're proof that even in the oldest corners of space, survival isn't just about longevity. Sometimes it's about knowing how to take what you need. Messier 80 is a cosmic magician's stage, a place where stars vanish right before our eyes. This dense globular cluster, packed with hundreds of thousands of stars, should be a predictable textbook case of stellar dynamics. Yet over decades of observations, astronomers have witnessed something unsettling. Stars that flicker out of existence without exploding, drifting away, or leaving any visible trace behind. It's as if the cluster has a hidden trapdoor swallowing stars whole. The most compelling evidence comes from before and after studies, when researchers compared Hubble Space Telescope images of Messier 80 taken years apart. They noticed something chilling. Certain stars, particularly bright, massive ones near the cluster's core, had simply disappeared. No supernova remnants, no drifting corpses like neutron stars or black holes. Just empty space where a star once burned. One theory suggests these stars might be colliding in the cluster's chaotic core. In such densely packed environments, close encounters between stars aren't just possible, they're inevitable. When two stars merge, the resulting explosion can be surprisingly faint, especially if it happens inside a cocoon of gas that masks the outburst. The merged star might then collapse directly into a black hole, bypassing the usual fireworks of a supernova. It's the cosmic equivalent of a building imploding inward, violent, but eerily quiet from the outside. But there's a darker possibility. Some researchers suspect these vanishings point to an unseen population of primordial black holes, ancient remnants from the universe's earliest moments, lurking invisibly in the cluster. These black holes, potentially weighing just a few times more than our Sun, could be drifting through Messier 80 like ghosts. When a star passes too close, the black hole's gravity could shred and consume it so quickly that the event emits barely any detectable light. The strangest part, this carnage might actually explain why Messier 80 looks younger than it should. The cluster's surviving stars appear unusually vibrant for their age, as if something has been selectively removing their older, dimmer neighbors. If primordial black holes or stellar collisions are indeed culling the herd, they might be leaving behind a population of stars that skews oddly youthful, a cosmic illusion created by invisible violence. Yet not all missing stars are victims. Some might be fugitives. Intense gravitational interactions near the cluster's core can fling stars outward at incredible speeds, ejecting them into interstellar space. These hypervelocity stars could be escaping undetected, their departures mistaken for disappearances. Messier 80's vanishing acts are more than just celestial curiosities, they're clues to the chaotic processes shaping star clusters over billions of years. Whether through collisions, black holes, or stellar ejections, this cluster is proving that even the most familiar corners of space can harbor secrets that defy our expectations. And with every star that vanishes, the mystery only deepens. Palomar 12 shouldn't be here. This ancient globular cluster, drifting at the fringes of our galaxy, is caught in a cosmic tug-of-war, one it's losing spectacularly. Unlike most clusters which orbit the Milky Way in near-perfect spheres, Palomar 12 is unraveling, its stars stretching into a shimmering ribbon called a tidal tail. This isn't just a slow disintegration, it's a full-blown stellar massacre, with the Milky Way's gravity ripping the cluster apart one star at a time. And the trail it's leaving behind is a chilling preview of what awaits many globular clusters in the distant future. The evidence is written in starlight. Telescopes have captured Palomar 12's elongated form, its outermost stars strewn across tens of thousands of light years like breadcrumbs. These aren't random ejections. They follow a precise curve, tracing the cluster's orbit like a comet's tail. Each star in this stream is a prisoner of gravity, torn from the cluster during close passes near the Milky Way's disk, where tidal forces act like cosmic grinders. The closer the cluster swings to the galaxy's dense core, the more stars it sheds, creating a stellar river that will eventually fade into the galactic background. But here's the twist: Palomar 12 isn't originally from the Milky Way. Chemical analysis reveals its stars are younger and richer in heavy elements than most globular clusters, suggesting it was born elsewhere, likely in the Sagittarius dwarf galaxy, a satellite galaxy our Milky Way has been devouring for billions of years. When the two galaxies collided, Palomar 12 was yanked away like a prize, only to be slowly digested itself. It's a cosmic irony, stolen by one galaxy, only to be destroyed by another. The real surprise lies in the tail's structure. Unlike smooth, predictable streams left by other clusters, Palomar 12's is lumpy, with clumps of stars clinging together against the tidal pull. Some researchers think these knots hint at the cluster's original structure, pockets of densely packed stars resisting disintegration longer than their sparse neighbors. Others suspect hidden black holes or dark matter might be anchoring these clumps, acting as gravitational glue. Yet the most haunting implication isn't about Palomar 12's past, it's about our galaxy's future. Every pass near the Milky Way's core strips away more stars, and simulations suggest the cluster has less than 1 billion years left before it's fully erased. Eventually, its tidal tail will dissolve into the galaxy's halo, leaving no trace of the cluster except a few wayward stars with unusual orbits. For astronomers, this slow-motion destruction is a rare opportunity to study how galaxies consume their smaller neighbors, one star cluster at a time. So while Palomar 12's fate is sealed, its unraveling tells a larger story, one about the brutal, beautiful forces that shape galaxies. And as we watch its stars scatter, we're witnessing a process that's as old as the universe itself, the relentless pull of gravity, rewriting the cosmic map one cluster at a time. Star clusters should be some of the loudest places in the universe when it comes to supernovas, those catastrophic explosions marking the death of massive stars. The physics is straightforward. When a star many times heavier than our Sun reaches the end of its life, it detonates with the energy of 1 billion suns, lighting up the cosmos with a burst of radiation and carving out vast shockwaves in the surrounding gas. Except in some clusters, astronomers are finding proof that supernovas happened, yet none of the usual aftermath, no glowing remnants, no expanding bubbles of hot gas. Just eerie silence where there should be cosmic fireworks. Take NGC 3603, a globular cluster packed with ancient stars. Spectroscopic studies reveal traces of elements like iron, titanium, and nickel materials forged only in the heart of supernova explosions. The amounts detected are staggering, enough to confirm that multiple massive stars must have blown apart here over the cluster's lifetime. But when researchers scan the same region with X-ray and radio telescopes, hunting for the telltale signatures of supernova remnants, they find nothing. It's like discovering an empty shell casing at a crime scene, but no bullet holes, no gunpowder residue, just the unsettling certainty that something violent occurred. So where did all the energy go? One possibility is that the supernovas were strangely cold, their explosions muffled by the cluster's dense environment. In a globular cluster, stars are packed so tightly that the debris from a dying star might slam into neighboring stars before it can expand into a visible remnant. Think of it like setting off a firework underwater. The energy's still there, but it dissipates quickly, absorbed by the surroundings. Some simulations suggest these failed supernovas could even collapse directly into black holes without the typical explosive show, their outer layers falling inward like a deflated balloon. But there's another, even stranger explanation. The missing supernovas might have been stolen. If a dying star is part of a tight binary system, its companion could intercept and absorb the explosion's energy, leaving no trace for telescopes to detect. Picture a supernova's shockwave hitting a neighboring star like a tsunami hitting a sponge. The energy doesn't vanish, but it's no longer visible as a distinct structure. In clusters like Omega Centauri, where binary stars are common, this could explain why some supernova evidence exists only in chemical fingerprints, not in glowing debris. Then there's the dark horse theory, primordial black holes. If these hypothetical relics from the early universe are lurking in star clusters, they might be acting as cosmic sponges, swallowing supernova debris before it can expand into a recognizable remnant. It's a radical idea, but if proven, it would solve two mysteries at once: the quiet supernovas and the unseen mass troubling so many clusters. What makes these ghostly explosions so fascinating isn't just their stealth, it's the implications for how star clusters evolve. If supernovas can occur without leaving remnants, we might be underestimating how many have happened throughout cosmic history. Entire chapters of a cluster's life story could be missing from the record, rewritten by physics we've only begun to glimpse. For astronomers, every silent supernova is a challenge to listen more closely, to search for the whispers hiding behind the universe's loudest explosions. NGC 6101 isn't just defying expectations about dark matter. It's also hiding something else, or rather, not hiding it. Among its many oddities, this cluster has a glaring shortage of binary star systems, those pairs of stars locked in mutual orbit. For a place so densely packed with stars, the absence of binaries is like walking into a crowded dance hall and finding almost no couples. And that's not just strange, it's a direct challenge to how we think star clusters form and evolve. Binary stars are supposed to be everywhere. In most globular clusters, at least 1 in 5 stars has a partner, with some regions harboring even more. These pairs form naturally during stellar birth, as collapsing gas clouds fragment into multiple objects. Yet in NGC 6101, the binary rate is less than half the usual number, maybe even lower. Telescopes have scoured the cluster for the telltale flickers or Doppler shifts of orbiting pairs, only to come up suspiciously empty. So where did all the binaries go? One possibility is as brutal as it is simple. The cluster's extreme environment ripped them apart. In a place this dense, stars don't just drift peacefully, they constantly jostle like commuters in a packed subway. Every close encounter between a binary system and a passing star can destabilize the pair, either widening their orbit until they drift apart or hurling one star away entirely. Over billions of years, this gravitational bullying could have left NGC 6101 with far fewer binaries than it started with, but there's a catch. Other clusters with similar densities still hold onto their binaries, suggesting something else is at work here. Some astronomers point to the cluster's unusual lack of dark matter. Without that extra gravitational glue, close encounters between stars might pack a stronger punch, making it easier to disrupt delicate binary orbits. It's like trying to keep hold of a partner's hand while getting shoved in a mosh pit. The less stability around you, the harder it is to stay connected. Then there's the timing problem. If binaries were systematically destroyed over time, we'd expect to see remnant single stars with unusual velocities ejected during the breakup. Yet NGC 6101 stars move more uniformly than expected, as if the binaries never existed in the first place. That's led to a radical alternative theory. Maybe this cluster formed under conditions that actively suppressed binary formation. Perhaps the gas cloud that birthed it was unusually hot or turbulent, preventing the fragmentation needed to create multiple stars close together. The implications stretch far beyond this one cluster. If binaries can go missing under certain conditions, it forces us to rethink how star clusters retain or lose their architectural blueprints over time. Are there other lonely clusters like NGC 6101 hiding in plain sight? Could this explain why some globular clusters seem to age differently than others? Every missing binary is a silent witness to processes we're only beginning to understand, a cosmic puzzle where the absence of something speaks louder than its presence ever could. Somewhere in the vastness of space, a mysterious signal blasts out with the power of 500 million suns, then vanishes in less time than it takes to blink. These are fast radio bursts, some of the universe's most perplexing phenomena, and for years their origins have been a total mystery. But recent discoveries suggest an unlikely culprit: star clusters. Not the serene, ancient globulars we're familiar with, but young, chaotic clusters teeming with stellar oddballs, and possibly the key to unlocking one of astronomy's greatest enigmas. The first clue came from a fast radio burst detected in 2020, traced back to a spiral galaxy over 3 billion light-years away. Nothing unusual there, except that the burst's precise location pointed straight to a vibrant star-forming region, the kind where massive, short-lived stars and dense neutron stars jostle for space. But the real breakthrough came when astronomers realized similar bursts had been linked to at least two other youthful clusters, places where stars are born, die, and collide at a dizzying rate. Suddenly, a pattern emerged. These explosive signals might be coming from environments where stellar chaos reigns. So what's the connection? One leading suspect is a type of neutron star called a magnetar, a city-sized remnant of a supernova, spinning wildly and wrapped in a magnetic field so strong it could strip the data from a credit card halfway across the Milky Way. In the crowded core of a young star cluster, magnetars could be jostled by passing neighbors, their crusts cracking under the strain and releasing bursts of energy that ripple across the cosmos. Think of it like a tectonic quake, but on a neutron star's surface, a starquake so violent it briefly outshines entire galaxies. Yet magnetars might not be acting alone. Some models suggest fast radio bursts could be the result of cosmic collisions, two neutron stars spiraling together, or a neutron star plowing through the debris of a recent supernova. In a dense cluster where stars are packed like commuters in a rush-hour subway, such smash-ups would be far more likely than in the quieter galactic outskirts. It's the perfect recipe for catastrophe. Take a volatile object, surround it with potential triggers, and wait for the fireworks. Here's where it gets even stranger. A handful of fast radio bursts repeat sporadically, defying the one and done pattern of most signals. These recurring bursts might originate from magnetars trapped in binary systems, their outbursts reignited every time they steal material from a companion star. Young clusters with their high binary rates and frequent interactions would be ideal nurseries for such repeat offenders, but the most tantalizing possibility involves something even more exotic: black holes. Some theorists argue that a fast radio burst could be the death cry of a star being shredded by a black hole's gravity, a scenario more probable in clusters where intermediate mass black holes might lurk unseen. If true, these fleeting signals could be our only glimpse of otherwise invisible cosmic predators. Whether the culprits are magnetars, collisions, or black holes, one thing's clear: star clusters are proving to be far more than just pretty collections of stars. They're cosmic laboratories, forging some of the universe's most extreme phenomena and occasionally hurling their secrets across space in bursts of radio waves we're only just beginning to decode. Every new fast radio burst traced back to a cluster isn't just solving a mystery. It's revealing how these stellar cities shape the universe's most violent, fleeting moments. In the heart of the globular cluster 47 Tucanae, something is emitting X-rays not from the expected sources like bright binaries or pulsars, but from seemingly empty patches of space. These ghostly signals flicker unpredictably, appearing and vanishing without warning, as if the cluster itself is breathing out bursts of high-energy radiation. The strangest part, many of these X-ray sources don't match any visible object, leaving astronomers to wonder: are we seeing the fingerprints of black holes or neutron stars that have gone rogue, hiding in plain sight? One leading theory points to isolated black hole stellar mass remnants drifting alone through the cluster's crowded core. Normally, black holes reveal themselves by siphoning gas from a companion star, heating it until it glows in X-rays. But in 47 Tucanae's dense environment, gravitational interactions could have stripped away those companions long ago, leaving the black holes dark and undetectable, except when they occasionally snatch a passing star or gas cloud. Imagine a predator lurking in tall grass, only visible when it briefly pounces. These capture events might explain the sporadic X-ray flashes, brief meals for otherwise invisible monsters. Then there's the neutron star possibility. Some of these ultra-dense remnants could be quiet pulsars, their beams of radiation not pointed at Earth, making them nearly impossible to detect until they flare up. Others might be neutron stars that cooled rapidly, Their surfaces no longer hot enough to emit X-rays unless they collide with debris or experience sudden crust quakes, triggering temporary outbursts. Chandra X-ray observatory data reveals some sources flaring to thousands of times their normal brightness in mere hours, then fading just as quickly, behavior that defies explanations tied to steady accretion. But the real enigma is the locations of these ghosts. Many X-ray sources cluster near 47 Tucanae's core, where stellar densities are so extreme that black holes and neutron stars should have either sunk deeper or been flung outward by gravitational slingshots. Their persistence in the mid-regions suggests something is anchoring them there, perhaps an unseen network of dark matter or intermediate mass black holes warping the cluster's gravitational landscape. Alternatively, these could be kicked objects, neutron stars sent careening by asymmetric supernova, now wandering the cluster like cosmic drifters. The implications stretch beyond this one cluster. If rogue black holes or neutron stars are indeed common in globular clusters, they could solve another mystery: why some clusters appear puffed up, their stars orbiting faster than visible mass should allow. Invisible remnants might be the missing gravitational glue, their combined heft shaping the cluster's dynamics without emitting light. Every ghostly X-ray flash could be a clue, a fleeting glimpse into the dark scaffolding holding these stellar cities together. So while 47 Tucanae's X-ray ghosts remain unidentified, they're far from silent. Each unexplained burst is a whisper from the cluster's shadowy underworld, a reminder that even in the brightest stellar crowds, the most intriguing players might be the ones we can't see at all. White dwarfs are supposed to follow strict cosmic rules: stellar embers that cool quietly after burning through their fuel, their masses neatly capped by physics. Yet in clusters like Messier 4 and NGC 6397, astronomers keep finding rebels, white dwarfs that weigh too much, defying the very limits that should govern their existence. These aren't just slightly overweight. Some tip the scales at nearly 1.4 times the mass of our Sun, skirting dangerously close to the threshold where they should catastrophically collapse into neutron stars. And no one can quite explain how they got there. The puzzle starts with how white dwarfs form. When a star like our Sun nears death, it sheds its outer layers, leaving behind a dense core of carbon and oxygen, a white dwarf. But there's a catch: the heavier the star, the more it fights this fate. Stars above 8 solar masses typically explode as supernovas, leaving neutron stars or black holes behind. For a white dwarf to reach 1.4 solar masses, it would need to start as a star far too massive to avoid self-destruction. Yet these cosmic rule breakers exist, and they're clustered, quite literally, in places where stars shouldn't be able to cheat the system. One theory involves stellar theft. In densely packed globular clusters, white dwarfs might gravitationally steal material from binary companions, inching their mass upward over time. Picture a cosmic pickpocket slowly draining a neighbor's wallet, except here, the currency is hydrogen gas, and the theft could push the white dwarf toward explosive instability. Hubble observations have caught a few of these suspects red-handed, their surfaces contaminated with hydrogen or helium siphoned from nearby stars. But even this can't fully explain the most extreme cases, where the white dwarfs are so massive they should have triggered supernovas long before reaching their current weights. Then there's the collision scenario. In the chaotic dance of a cluster's core, 2 white dwarfs might spiral together and merge, their combined mass vaulting past the usual limits. Simulations show these mergers could produce white dwarfs nudging 1.4 solar masses, but they'd also be unstable, prone to rapid collapse. Yet the overweight dwarfs in Messier 4 show no signs of impending doom. Their surfaces are calm, their cooling rates normal, as if they've somehow stabilized at masses that should be impossible. The most tantalizing clue lies in their composition. Some of these massive dwarfs are rich in oxygen and neon elements forged under extreme pressures, hinting at violent pasts. Others sport carbon-dominated atmospheres, suggesting they might be the remnants of stars that almost went supernova but stalled at the last moment. It's as if these stars found a loophole in stellar physics, a way to cram in extra mass without triggering the usual fireworks. What makes these outliers so fascinating isn't just their defiance of expectations, it's what they reveal about the extremes of stellar evolution. If white dwarfs can balloon beyond their theoretical limits, what else have we misunderstood about how stars die? Every overweight dwarf is a test case, a challenge to our models, and perhaps a preview of fates that await other stars in the universe's most crowded neighborhoods. For now, they remain Enigma's stellar rebels that refuse to play by the rules. Most planets in the universe should be tethered to stars, locked in orderly orbits around their suns. At least that's what we used to think. But star clusters have been quietly upending that assumption, revealing a hidden population of rogue planets drifting untethered through the void. These aren't just rare strays. In places like the Trapezium cluster in Orion, astronomers have detected hundreds of these free-floating worlds, some weighing in at several times Jupiter's mass. Their existence isn't just surprising, it's rewriting the playbook on how planets form and survive in the universe's most chaotic environments. The first shock came from infrared surveys, which picked up the faint heat signatures of objects too small to be stars yet too cold to be brown dwarfs. These rogue planets emit no light of their own, but their residual warmth betrays their presence, especially in young clusters where they haven't had time to cool completely. Some, like those in the Sigma Orionis cluster, are barely a few million years old cosmic infants that should still be nestled in the disks of gas and dust around newborn stars. Yet there they are, adrift in the darkness, untethered from any stellar parent. So how did they get there? One theory suggests violent ejections. In the crowded cores of star clusters, gravitational tugs of war between neighboring stars could fling planets outward like stones from a slingshot. Simulations show that a close encounter between two stars might destabilize an entire planetary system, sending some worlds careening into interstellar space while others spiral into their host stars. It's a brutal game of cosmic pinball, and the losers become permanent exiles. But here's the twist, not all rogue planets are escapees. Some might have formed alone, collapsing directly from isolated pockets of gas and dust like miniature stars. These failed stars could blur the line between planet and brown dwarf, challenging our definitions of what a planet even is. In clusters like Rho Ophiuchi, where star formation is still ongoing, telescopes have spotted dense knots of gas that could be the birthplaces of these free-floating worlds, objects that never had a star to call home in the first place. The implications are staggering. If rogue planets are common, they could outnumber stars in some clusters, a hidden population of orphans drifting unseen between the light. Some might even harbor subsurface oceans kept liquid by tidal forces or radioactive decay, making them potential havens for life in the coldest reaches of space. And because they don't orbit stars, they'd avoid deadly flares or stellar radiation, offering stable, if frigid environments for billions of years. Yet the biggest mystery isn't their existence, it's their survival. Planets ejected from their systems should freeze rapidly, their atmospheres collapsing into icy shells. But some rogues, like those in the Upper Scorpius Association, show signs of lingering heat and even auroras, suggesting magnetic fields or residual volcanic activity. How they retain this energy without a star's warmth remains an open question, one that could reveal new physics governing planetary evolution. For astronomers, these drifters are more than just curiosities. They're proof that planet formation is messier, more dynamic, and far more creative than we ever imagined. Every rogue world discovered forces us to reconsider the boundaries of planetary science, reminding us that the universe doesn't always follow the neat categories we try to impose. In star clusters where gravity's chaos reigns supreme, the rules are still being written and the planets, it seems, are playing by their own. Messier 3 is home to some of the most rebellious binary stars in the galaxy, pairs that don't just orbit each other, but do so at angles so steep they seem to defy gravity itself. Normally, binaries in a globular cluster follow orderly paths, their orbits aligned with the cluster's rotation like cars on a well-designed roundabout. But here, astronomers have spotted systems tilted as much as 90 degrees, spinning wildly sideways as if thrown off kilter by some unseen cosmic hand. These misaligned orbits aren't just visual oddities, they're clues to the cluster's turbulent past. One leading theory suggests violent encounters are to blame. In Messier 3's densely packed core, stars jostle constantly, and a close brush with a passing neighbor can yank a binary system off its original axis like a cue ball striking a spinning top. Over billions of years, these gravitational shoves add up, leaving some pairs permanently askew. Hubble observations reveal particularly dramatic cases where one star loops almost perpendicular to its partner's spin, creating a celestial seesaw that challenges our models of orbital stability. Yet collisions might not be the only culprit. Some researchers speculate these tilted binaries could be immigrants, captured from outside the cluster during a long-ago galactic merger. Stars formed elsewhere might carry unique angular momentum, their orbits already inclined before being snatched into Messier 3's gravitational embrace. Chemical analysis supports this idea. A handful of these rebellious pairs show unusual metal content, hinting at origins in a smaller, long-devoured galaxy. The real puzzle lies in their survival. In most environments, such extreme tilts would destabilize over time, smoothed out by tidal forces or gravitational interactions. But Messier 3's unique dynamics seem to preserve these oddities like a museum of cosmic misfits. Some systems even show signs of precession, their tilted orbits slowly wobbling like a spinning top about to fall, yet somehow maintaining their defiance for eons. What makes these tilted binaries invaluable isn't just their strangeness, it's what they reveal about the hidden forces shaping star clusters. Their skewed paths trace the ghostly fingerprints of past collisions, mergers, and close calls, offering a forensic record of the chaos simmering beneath the cluster's serene glow. For astronomers, every misaligned orbit is a question. How many more clusters harbor these cosmic renegades, and what other rules might they be breaking? Messier 3's sideways stars aren't just anomalies, they're proof that even in the oldest corners of the universe, gravity's dance never follows the steps we expect. In the heart of the ancient globular cluster NGC 6397, astronomers stumbled upon a cosmic mystery with implications stretching back to the birth of the universe itself. Stars that are missing a key ingredient. Lithium, one of the three elements forged in the explosive aftermath of the Big Bang, should be abundant in these elderly stars. Instead, it's almost entirely absent, as if someone siphoned it away over billions of years. This isn't just a minor discrepancy, it's a direct challenge to our understanding of how the first elements formed and how stars evolve. The puzzle begins with nucleosynthesis, the process that created the universe's earliest elements. Minutes after the Big Bang, the cosmos was a seething cauldron of protons and neutrons colliding to form hydrogen, helium, and trace amounts of lithium. Models predict that stars born from this primordial material, like those in NGC 6397, should preserve at least some of that original lithium in their outer layers. Yet spectroscopic analysis reveals levels hundreds of times lower than expected, a gap so vast it can't be blamed on measurement error. It's like finding a library where every copy of a specific book has been systematically removed, leaving empty shelves where knowledge should be. So where did the lithium go? One theory points to stellar interiors as the culprit. As stars age, convection currents churn their outer layers, dragging lithium down into hotter regions where temperatures exceed 2 million degrees, enough to destroy it in nuclear reactions. This lithium sink effect could explain the depletion in Sun-like stars, but it falters when applied to NGC 6397's cooler red giants, where lithium should remain safely near the surface. Somehow, even these stars have been scrubbed clean. Then there's the possibility of external forces. Globular clusters are dynamic environments where stars brush past one another in gravitational dances. Could close encounters have stripped away lithium-rich outer layers, leaving behind depleted cores? It's plausible, but observations show neighboring clusters with similar densities still retain their lithium, suggesting NGC 6397's deficit isn't just a product of stellar crowding. The most tantalizing explanation involves a process we've yet to observe directly: exotic physics in the early universe. Some theorists propose that certain dark matter particles, if they interacted with primordial lithium, could have accelerated its destruction before the first stars formed. Others wonder if our models of Big Bang nucleosynthesis are incomplete, missing a pathway that suppressed lithium production from the outset. Both ideas are controversial, but the sheer scale of the discrepancy demands radical thinking. What makes this mystery so compelling isn't just the missing element, it's the stakes. Lithium is a cornerstone of our cosmic origin story, a fingerprint of the universe's first moments. If we can't account for its absence in places like NGC 6397, it might mean rewriting parts of that story. Every lithium-poor star in this cluster is a silent witness to processes we're only beginning to imagine, a reminder that even the oldest objects in the cosmos still have secrets to share. Westerlund 2 should be a textbook example of a young star cluster, a nursery of massive, hot stars carving out their space in the cosmos. But something about this stellar neighborhood doesn't add up. Surrounding its brilliant stars are vast, glowing structures of ionized gas, twisting into shapes that defy the usual sculpting forces of stellar winds and radiation. These aren't just random clouds, they're intricate, almost architectural formations, glowing with an intensity that suggests an invisible hand is at work. And the closer astronomers look, the stranger the story gets. At the heart of the mystery is the gas itself. Young clusters like Westerlund 2 are known to produce fierce ultraviolet radiation, which strips electrons from nearby hydrogen atoms, causing the gas to glow in characteristic red hues. But here, the ionization patterns don't match the star's output. Some filaments stretch far beyond where the cluster's radiation should reach, while others glow too brightly, as if amplified by an unseen energy source. It's like holding a flashlight in a dark room and finding patches of light where the beam doesn't point. Something else must be illuminating the scene. One leading suspect is hidden supernova remnants. If a massive star in the cluster exploded unnoticed centuries ago, its shockwave could have rippled through the surrounding gas, compressing and heating it into these bizarre shapes. Chandra X-ray observatory data reveals faint hints of high-energy material mixed into the structures, supporting this idea. But there's a problem: the gas is too organized. Supernova remnants typically create chaotic, expanding bubbles, not the delicate, ribbon-like filaments seen here. Then there's the magnetic field theory. Recent radio observations suggest Westerlund 2's gas is laced with powerful magnetic fields, far stronger than expected for a cluster this young. These fields could act like invisible wires, channeling the ionized gas into precise, glowing pathways. Picture a cosmic version of neon tubing, where magnetic forces shape the light instead of glass. If confirmed, this would mean the cluster's environment is far more magnetically violent than we thought, with forces capable of corralling gas on scales spanning light years. But the most tantalizing clue lies in the cluster's periphery. Some of the glowing structures align eerily with the edges of nearby molecular clouds, dense, cold regions that shouldn't be interacting with the cluster at all. This has led to a radical idea. Westerlund 2 might be leaking radiation through pre-existing tunnels in the interstellar medium, like light seeping through cracks in a wall. These tunnels could have been carved by ancient stellar winds or even the gravitational pull of passing dark matter clumps, creating a labyrinth that focuses and distorts the cluster's energy in unexpected ways. What makes Westerlund 2's glowing gas so captivating isn't just its beauty, it's the reminder that even the brightest stellar factories are full of shadows, places where our understanding of physics hits its limits. Every twisted filament is a question. Are we seeing the aftermath of forgotten explosions, the handiwork of invisible forces, or something entirely new? Until we solve it, this young cluster's glow will remain one of the most mesmerizing and perplexing sights in the cosmos. Omega Centauri, the Milky Way's largest globular cluster, has always been a cosmic rebel, but even by its unruly standards, the stars moving backward stand out as screaming anomalies. These aren't just stars with slightly tilted orbits, they're full-on renegades circling the cluster's core in the exact opposite direction of the overwhelming majority. It's like watching a busy highway where every car drives west except for a handful speeding east, defying every rule of traffic, and their existence isn't just a curiosity, it's a smoking gun pointing to a cataclysmic past. To understand why these backward stars are so shocking, picture how star clusters form. Gravity pulls stars into a collective whirl like water spiraling down a drain, with most orbits aligning neatly with the cluster's rotation. Finding stars that break this flow suggests one of two possibilities. Either they were born under bizarre circumstances, or something violently yanked them off course long ago. In Omega Centauri's case, the evidence leans heavily toward the latter. Spectroscopic studies reveal these rebellious stars aren't just moving backward, their chemical makeup often differs sharply from their neighbors, as if they were forged in a completely different environment. That's where the plot thickens. Many astronomers now suspect Omega Centauri wasn't always a globular cluster. It might have started as the heart of a dwarf galaxy, a smaller system shredded and absorbed by the Milky Way billions of years ago. During that chaotic merger, stars from the doomed galaxy could have been flung into retrograde orbits, their paths scrambled by gravitational turbulence. Imagine tossing a handful of confetti into a whirlpool. Some pieces will inevitably swirl the wrong way. These backward stars might be the last survivors of that galactic feast. Their stubborn orbits a silent testimony to the violence that birthed them. Yet there's another, even wilder explanation: black hole billiards. Omega Centauri is thought to harbor an intermediate mass black hole at its core, and simulations show such an object could catapult stars into backward orbits during close encounters. A star swinging too near the black hole might get a gravitational slingshot so powerful it flips its trajectory entirely, like a pinball ricocheting off a bumper. Some backward stars even show signs of hypervelocity, speeds so extreme they'd almost escape the cluster entirely, were it not for the collective gravity holding them in check. But the real twist, these stellar contrarians might be shaping Omega Centauri's future as much as they reflect its past. Their chaotic orbits inject turbulence into the cluster's dynamics, stirring the stellar population like a spoon in a swirling cup of coffee. Over millennia, this could prevent the cluster from settling into a stable, predictable rotation, keeping it forever unbalanced. For astronomers, that's a gold mine, a chance to study how gravitational chaos unfolds in real time with these backward stars as the prime agitators. So while they might seem like cosmic misfits, these rogue stars are anything but random. They're time capsules, forensic evidence, and celestial wrecking balls all in one, proof that even in the densest stellar cities, the past never fully fades. Every backward orbit is a scar, a reminder of the chaos that built the universe we see today. Deep in the faint glow of the Fornax dwarf galaxy, astronomers have stumbled upon something that shouldn't be visible: threads of darkness weaving through the cosmos like invisible spider silk. These are the so-called dark matter filaments, ethereal strands supposedly connecting star clusters across vast distances. If confirmed, they'd be the first direct evidence of the universe's hidden scaffolding, the elusive structure that theorists say binds galaxies together. But here's the catch: we can't actually see dark matter. So how do we know these filaments exist, and why is Fornax the only place they've been spotted? The hunt began with ghostly distortions in starlight. As telescopes mapped the motions of stars in Fornax's globular clusters, they noticed something peculiar. The clusters weren't just drifting randomly. Their movements suggested an unseen gravitational tether, a force subtly herding them along invisible paths. Computer simulations reinforced the idea, showing that dark matter ought to form delicate bridges between clusters, funneling stars along specific routes like cars on a cosmic freeway. Yet for decades, these filaments remained purely theoretical until a team analyzing Hubble data noticed faint, linear arrangements of stars stretching between Fornax's clusters, aligning eerily with where dark matter's grip should be strongest. But skepticism runs deep. Some researchers argue these stellar trails could be tidal streams, debris left behind when smaller clusters were torn apart by Fornax's gravity. Others point to the staggeringly low odds of dark matter's subtle influence being detectable in such a faint galaxy. After all, if these filaments permeate the universe, why haven't we spotted them elsewhere? The answer might lie in Fornax's unique history. Unlike most dwarf galaxies, it's relatively isolated, spared the gravitational harassment that scrambles stellar arrangements in busier galactic neighborhoods. This pristine environment could preserve dark matter's delicate architecture, leaving its filaments undisturbed for billions of years, like finding a fossil frozen in perfect condition. The most tantalizing clue comes from the filament's geometry. They're not random wisps but surprisingly straight, spanning tens of thousands of light years with a uniformity that defies chance. Simulations suggest dark matter filaments should act like cosmic conveyor belts, channeling gas and even entire star clusters along their lengths. Intriguingly, Fornax's clusters show signs of synchronized movement, as if being guided by unseen rails. If dark matter is the conductor, it would solve another mystery: why some clusters here orbit in lockstep despite being too far apart to influence each other directly. Yet the debate is far from settled. Alternative theories propose these alignments could be echoes of a past galactic collision, or even artifacts of how we're interpreting the data. Without direct detection of dark matter, something that's eluded scientists for decades, these filaments remain in the realm of compelling circumstantial evidence. But that's what makes Fornax's dark threads so electrifying. They're not just potential proof of the universe's hidden framework, they're a challenge. Either we're glimpsing dark matter's handiwork for the first time, or we're being forced to rethink everything we thought we knew about gravity itself. For now, Fornax's filaments hover between discovery and Enigma, a cosmic riddle written in the negative space between the stars, and whether they're confirmed as dark matter's signature or dismissed as a celestial illusion, one thing's certain: they've opened a new front in our quest to understand the invisible forces shaping the cosmos. In the heart of Messier 4, one of the Milky Way's oldest globular clusters, there are stars that refuse to stay dead. These aren't your typical stellar remnants, they're cosmic zombies resurrected from the brink of destruction after violent supernova explosions should have wiped them out completely. What makes them so baffling isn't just their survival, it's the way they've clawed their way back into existence, defying the very laws that govern how stars die. Take the case of a star catalogued as M4CK3, a pulsar spinning hundreds of times per second, its surface bristling with magnetic fields strong enough to atomize matter from light years away. By all accounts, this object shouldn't exist. Its rapid spin and intense energy suggest it was born from a supernova, the kind of explosion that typically leaves behind either a silent neutron star or a black hole. Yet here it is, pulsing with relentless energy, as if the star's death throes somehow reignited its corpse. The secret might lie in a sinister partnership. Many of these zombie stars are locked in binary systems with ordinary stars, their gravitational pull siphoning gas from their living companions. As this stolen material rains down onto the neutron star's surface, it triggers violent thermonuclear explosions burst so powerful they temporarily outshine entire star clusters. These aren't just minor flare-ups, they're full-scale resurrections with the dead star feeding off its neighbor to sustain a grotesque parody of stellar life. Astronomers call these events pulsar rejuvenation, but a more fitting term might be cosmic vampirism, a predator-prey relationship playing out on an unimaginable scale. Then there's the even stranger phenomenon of born-again stars. In 2019, Hubble spotted a star in Messier 4 that had undergone a second helium flash, a late-stage thermal pulse that typically happens only once in a star's lifetime. This elderly star, having already shed its outer layers and begun cooling into a white dwarf, suddenly reignited, puffing up like a bellows and glowing with newborn intensity. It's as if the star, having reached the end of its life, somehow found a hidden reservoir of fuel and decided to burn it all in one last defiant blaze. The implications are staggering. If stars can cheat death or at least delay it through violent means, it forces us to rethink the boundaries of stellar evolution. Could other dead stars in clusters be secretly active, hiding their energy output until the right conditions trigger them back to life? And what does this mean for the chemical enrichment of clusters, where supernova debris is supposed to seed new generations of stars? Messier 4's zombies are more than just celestial oddities. They're a challenge to our understanding of how stars live, die, and apparently sometimes refuse to do either. Every flicker from these undead stars is a reminder. In the crowded stellar graveyards of globular clusters, the line between life and death is far blurrier than we ever imagined. NGC 2808 isn't just breaking the rules, it's rewriting the script on stellar aging. This globular cluster, one of the Milky Way's most massive, hosts an impossible population of blue stars, burning far hotter and brighter than its ancient age should allow. Normally, a cluster this old, nearly 12.5 billion years, should be dominated by cool red giants and dim white dwarfs, its original blue stars long since burned out. Yet here they are, shining with the vigor of cosmic teenagers, their presence a glaring contradiction to every model of stellar evolution. The mystery begins with color. Blue stars are the universe's high-performance sports cars, massive, fuel-guzzling, and short-lived. Most exhaust their hydrogen in just tens of millions of years before exploding as supernova. So finding them in a cluster that predates Earth by over 8 billion years is like stumbling upon a living dinosaur. Early observations with the Hubble Space Telescope revealed not just a handful of these anomalies, but 3 distinct groups of blue stars, each burning at different temperatures as if they'd been born in separate cosmic epochs. One theory points to stellar collisions as the culprit. In NGC 2808's densely packed core, stars are crammed so tightly that close encounters aren't just likely, they're inevitable. When 2 stars collide, their combined mass can reignite nuclear fusion, creating a rejuvenated blue straggler that outshines its neighbors. But while this explains some outliers, it can't account for the sheer volume of blue stars here. Simulations show even the most chaotic clusters shouldn't produce this many stragglers, yet NGC 2808's core gleams with them. Then there's the helium factor. Spectroscopic studies reveal many of these blue stars are bizarrely rich in helium, their outer layers stripped of hydrogen by some unknown process. This points to a darker possibility, cosmic cannibalism on an industrial scale. In binary systems where one star siphons gas from its partner, the thief's hydrogen-rich outer layers can mask a helium-dominated core, creating the illusion of youth. Some astronomers suggest NGC 2808's extreme density turbocharges this theft, with multiple generations of stars stealing fuel from one another in a chain reaction of stellar vampirism. But the real shock came when researchers noticed these blue stars aren't randomly scattered, they're clustered in specific orbits. hinting at multiple waves of star formation in a place where new stars shouldn't exist. One provocative theory suggests the cluster retained reservoirs of gas long after its initial birth, allowing sporadic bursts of new stars to form from recycled material. Others propose it might have cannibalized smaller clusters, importing fresh blue stars like cosmic trophies. The most radical explanation, NGC 2808, might not be a true globular cluster at all, but the stripped nucleus of a dwarf galaxy. Its unusual mass and complex stellar populations align with what we'd expect from a galactic core, where ongoing star formation could persist for billions of years longer than in typical clusters. If true, it would make this celestial rebel not just an oddball, but a fossil of a long-dead galaxy hiding in plain sight. What makes these blue stars so valuable isn't just their defiance, it's the window they offer into stellar survival tactics. By studying how they cheat time, we're glimpsing processes that could rewrite our understanding of star formation in the most extreme environments. NGC 2808 isn't just a cluster with too many blue stars. It's a cosmic laboratory where the rules of aging are being broken, one luminous rebel at a time. NGC 3201 is playing a cosmic game of hide and seek, and the black holes here are winning. This globular cluster, located about 16,000 light-years away in the constellation Vela, behaves as if it's harboring multiple invisible predators, their presence betrayed only by the terrified motions of stars fleeing unseen dangers. Unlike textbook black holes that announce themselves with X-ray flares or radio jets, these remain stubbornly silent, emitting no detectable radiation. They're cosmic ghosts, felt but not seen, rewriting the rules of how black holes can hide in plain sight. The first clue came from Hubble's sharp-eyed observations of stellar motions. Astronomers noticed several stars whipping around at breakneck speeds, up to 200,000 miles per hour following tight, looping orbits around. Nothing, no visible companion, no glowing accretion disk, just empty space with enough gravitational punch to fling a sun-sized star like a slingshot pellet. The math was inescapable. Each of these frenzied stars must be orbiting a black hole roughly 4 to 5 times more massive than our Sun. Yet when scientists pointed every available telescope toward these coordinates, hunting for the telltale flicker of infalling matter or distorted spacetime, they found only darkness. This discovery flips traditional black hole detection on its head. Normally, we spot these cosmic vacuums by their messy eating habits, superheated gas screaming in X-rays as it spirals toward the event horizon. But NGC 3201's black holes seem to be fasting, either starved of nearby material or consuming it so efficiently they leave no crumbs. Some researchers speculate these might be dark binaries, where the black hole's companion is a compact object like a white dwarf, their union producing no detectable light. Others wonder if we're seeing the aftermath of a grisly feast, black holes that have already stripped their stellar partners bare and now drift undetectably among the cluster's stars. The implications ripple outward. Globular clusters were long thought to expel most black holes through gravitational interactions, leaving only a handful behind. But if NGC 3201's invisible population is any indication, these clusters might be teeming with dark remnants, dozens, even hundreds lurking unnoticed. This could solve the lingering mystery of why some clusters appear puffed up, their stars moving faster than visible mass can explain. The missing gravity might belong to these hidden beasts, their collective weight sculpting the cluster from the shadows. Yet the real enigma isn't just their stealth, it's their formation. How did so many stellar mass black holes avoid merging or getting ejected during the cluster's violent youth? One provocative theory suggests they formed later, during chaotic three-star encounters that funneled extra mass into collapsing cores. Another posits they migrated inward over eons, drawn to the cluster's heart like spiders to a web center. Each scenario paints NGC 3201 as a black hole nursery, where the universe's darkest objects aren't rarities but dominant players in a hidden hierarchy. The search for answers has turned this unassuming cluster into a living laboratory. Astronomers now scrutinize every erratic star, every subtle gravitational ripple for traces of the unseen. Because in the end, NGC 3201's greatest lesson might be this: sometimes the universe's most powerful forces leave no trace at all except in the terrified orbits of those that stray too close. The Hyades cluster has always been one of the most familiar sights in our night sky, a V-shaped swarm of stars so close they've guided sailors for millennia. But behind that tranquil appearance lies a cosmic crime scene, where something massive has left gravitational fingerprints in the star's very positions. Astronomers have detected strange ripples moving through the cluster, waves of stars displaced from their expected orbits, like the wake of a ship slicing through water. These aren't random fluctuations, they're organized disturbances that suggest the Hyades survived a violent encounter we can't see, but whose echoes still shape the cluster today. What makes these ripples so fascinating is their precision. Unlike the chaotic orbits in most clusters, the Hyades disturbances form clear spiral patterns when mapped in 3D. Stars subtly shifted outward in some regions, pulled inward in others. Gaia Space Telescope data reveals these waves extend nearly 15 light-years across the cluster, with the most affected stars displaced by up to 10% from where stellar dynamics predict they should be. It's as if the entire cluster shuddered from some ancient impact, and we're seeing the lingering reverberations. The prime suspect, a close brush with a massive object, likely one of the Milky Way's dark matter clumps or a rogue molecular cloud. As the invisible interloper passed through the Hyades, its gravity would have tugged stars outward in its wake, creating a ripple effect that propagated through the cluster. Simulations show the timing aligns with a potential encounter roughly 130 million years ago, though no visible trace of the perpetrator remains. Some researchers speculate the culprit might have been an ancient globular cluster long since torn apart by the Milky Way's tides, its stars now scattered too thinly to recognize. Yet there's another possibility: the ripples could be self-inflicted. The Hyades is slowly dissolving, its outer stars stripped away by galactic tides. As the cluster loses mass, its gravitational equilibrium shifts, potentially triggering internal waves that redistribute stars in these observed patterns. It would be like watching a melting iceberg crack and groan as it adjusts to its changing weight, only played out over millions of years and spanning light years of space. The most tantalizing clue comes from the cluster's youngest stars. While the Hyades is generally ancient, a handful of stellar outliers appear suspiciously youthful, as if they formed from gas compressed by these very ripples. If confirmed, it would mean the disturbance didn't just rearrange the cluster, it sparked new life within it, turning gravitational chaos into stellar rebirth. For astronomers, these ripples are more than just curiosities, they're forensic evidence. By studying how the disturbance propagates, we can reverse engineer the properties of whatever caused it, probing the Milky Way's invisible substructure in ways no telescope can directly observe. The Hyades' gentle sway might be our best window into the unseen forces constantly reshaping our galactic neighborhood. A reminder that even the most familiar star patterns are dancing to rhythms we've only begun to hear. The Hercules globular cluster, known as Messier 13, contains over 300,000 stars packed into a dense sphere just 145 light-years across. But buried within this ancient stellar city, a single sun named KC 8462852 briefly ignited one of astronomy's most heated debates, not for what it was, but for what it wasn't. In 2015, the Kepler Space Telescope caught this star doing something inexplicable. Over several years, its light dipped by up to 22% in irregular, jagged patterns, nothing like the smooth curves of a transiting planet. The dimming events lasted anywhere from 5 to 80 days with no apparent rhythm or repetition. It was as if something vast and geometrically complex was passing in front of the star, blocking its light in ways no natural phenomenon could explain. The most infamous hypothesis came from astronomer Jason Wright, who suggested the dimming might resemble what we'd expect from a Dyson swarm, a hypothetical megastructure built by an advanced civilization to harness a star's energy. Imagine a network of solar-collecting satellites or orbiting habitats, so dense they occasionally eclipse their host star in chaotic, non-repeating patterns. The idea was radical, but for a brief moment it seemed plausible. After all, M13 is over 12 billion years old. If any cluster had the time to nurture an interstellar civilization, this would be the place. But nature often outpaces our wildest speculations. Further observations revealed the star's light was also dimming at longer wavelengths, a detail that clashed with the megastructure theory. Solid objects, whether alien constructs or planets, block all light equally. Instead, the wavelength-dependent dimming pointed to something far stranger, vast clouds of fine dust, likely from a recent collision between planets or swarms of comets. These particles would scatter blue light more than red, creating the exact spectral fingerprints Kepler detected. Yet the mystery didn't end there. Even after accounting for dust, the star's most extreme dimming events remained poorly explained. Some researchers proposed a shattered planet, a world torn apart by gravitational tides, its debris field now tracing an erratic orbit. Others pointed to M13's dense environment, where close stellar encounters could fling entire planetary systems into disarray, creating chaotic dust clouds that eclipse their star in unpredictable ways. The truth may be even more fascinating than fiction. In 2021, the Hubble Space Telescope spotted evidence of a massive asteroid family around another M13 star, suggesting this cluster might be a demolition derby for planetary debris. Gravitational jostling could constantly stir up these wreckage fields, creating transient shadows that flirt with the boundaries of what we consider natural. What began as a search for aliens became a masterclass in cosmic humility. M13's peculiar star reminds us that the universe doesn't need extraterrestrial engineers to produce wonders, just time, gravity, and a little chaos. And while the megastructure hypothesis faded, its legacy endures, a lesson that sometimes the most alien things in space are the ones nature builds all on its own. From pulsars that cannibalize their neighbors to star clusters that defy dark matter itself, these 30 discoveries prove one thing: the universe is far stranger than we ever imagined. Who would have thought ancient globular clusters could harbor diamond planets, or that some stars could cheat death by stealing their companions' lifeblood? These aren't just quirks of space, they're cosmic revolutions, forcing us to rewrite the rules of stellar evolution, gravity, and even time itself. Every mystery we've uncovered reveals how much we still don't understand, turning what we thought were simple collections of stars into dynamic, chaotic, and utterly unpredictable worlds. Take Omega Centauri's runaway stars, speeding through space at impossible velocities, or Palomar 12, unraveling like a cosmic ball of yarn as the Milky Way devours it. Then there's the eerie silence of M15's missing black hole, or the way NGC 6101 flouts all expectations by existing without dark matter's gravitational glue. These discoveries don't just add to our knowledge, they break it, demanding we rethink everything from how planets form to what lurks in the darkest corners of star clusters. And the best part, this is just the beginning. For every mystery solved, a dozen more take its place. Why do some clusters lack red giants? What's igniting fast radio bursts in young stellar nurseries? Each unanswered question is an invitation to explore, to theorize, to keep looking up and wondering what else is out there, hiding in plain sight. So now it's your turn. Which of these cosmic enigmas blew your mind the most? Was it the vampire stars of NGC 188 draining their neighbors to stay young? or the ghostly X-ray sources in 47 Tucani, hinting at invisible black holes. Drop your favorite in the comments. We're all detectives in this grand celestial mystery. And if you're hungry for more deep space wonders, don't forget to subscribe and hit that notification bell. The universe is full of secrets, and together we're just getting started uncovering